Okay, I think we should start. Thank you everyone for turning up to our first Sydney Nano Distinguished Lecture. This is the initiative we want to have throughout the year with lots of very established, well-known researchers such as Yuri. So we have Yuri Kivshar from Professor Yuri Kivshar from Australian National University today here. He is the head of Nonlinear Physics Center at Australian National University. He is perhaps well known to everyone here in this room, but just to follow the protocol, his research interests include nonlinear physics, metamaterial, and nanophotonics. He's the fellow of Australian Academy of Science and Optical Society. He basically have won many awards, like every award that is in the field, like Light Medal in Australia, and the State of Prize in Science from Ukraine, and Home of Research Award from Germany. So he's here to present our first distinguished lecture at Sydney Nano on all-dielectric resonant metal optic and nanophotonics. So without any further ado, can you please join me to thanks Yuri for his time in this presentation.
Thank you. Oh. What's happening? Not working. Ah. Okay. Thanks for coming. I thank Ben and for invitation and Domi for entertaining me this morning with the breakfast and all explaining philosophy and nano. I was a long time ago when I saw many empty rooms. Now it's very impressive development and also quite interesting development in Canberra. So formally I'm head of the Nonlinear Physics Center. So it's now 5 independent groups and I have my own group with recently fabricated lasers by Barry Luther Davis, as you understand, for half price, and a lot of interesting activities. So what I'm going to talk about is a new field, which hopefully I was at the very beginning of that. It was very lucky. And I will try to explain what is the origin and give you some food for further research. And of course, we open for collaboration and for new ideas. If you bring new ideas, we're happy to consider them and help you. And anyway, I go ahead. Remote is not working. I told you I should bring my own. All right, thank you. Hopefully it will be. Okay, so I start from metamaterials. So many people definitely in this audience knows about metamaterials. So these are artificial structures composed of different elements. And of course, one of the traditional elements, so-called electric atoms, when we excite electric dipole resonances. And for metamaterials specifically, we need magnetic atoms when we excite magnetic dipole resonances. So all together, we combine in the structures. That's how this metamaterial is made. And each separate element brings some local microscopic response. And we are talking about macroscopic parameters. So basically, we're looking at some average parameters like initially was suggested by Vesilago and Pendry. And the idea of all this field is actually to introduce any parameters on that space mimic in nature, but on different scale, and basically design structures with arbitrary required magnetic and electric response. That's, of course, important message for optics application to take advantage of both electric and magnetic responses. This is, of course, very well known in radio physics and microwaves, but in optics is still majority of effects are driven by electric field and electric dipole resonances. But in metamaterials, the most important message is that we have structures which have this opportunity to control magnetic response. So this is splitter and resonator, as was suggested by John Pendry a long time ago, and it brings possibility to engineer magnetic response of the structures for electrons which are moving in metals and create this magnetic response. But now it's time to move to different field because these structures use metals and requires some average parameters in this field, which I called meta optics. Is something what again meta, but it brings some different type of meaning. So what is meta optics? Of course, you can go to conference and see many titles get meta optics from different famous people, even for different applications. But in my life, first time when I came across the field was from our friend, which you know very well, Ross McFedron, who still probably here, working here like emeritus professor. And we were writing that paper with Boris and Ross in 2011, and Ross suggested the title, Meta Optics. I objected, said, Ross, what kind of meta optics you're talking about? 2011, can you imagine? There was no single optical metamaterial yet. And I asked recently Ross why he suggested the title, and that's his answer. He basically said that he wanted to combine some optics application, probably because of Boris's fibers. I don't know how it came to mind, but it was not optics anyway, it was terahertz, right? So, but that's how it appeared, and now it's really makes sense because we move to the point when this is really can be brought to optics applications. So the key things in that approach is the Mie theory. Mie theory is very old, and in Germany people know Mie for this Mie modules, but I'm not talking about that. I'm talking about the theory of suggested by Mie. If you look at the year, it's incredibly old. Of course, it was kind of first solution when Mie solved Maxwell equation for the problem when the spherical particles as electromagnetic waves are scattered, and that he solved it for these crocodiles, which everybody now can put in the Mathematica. That time was, of course, heroic effort. And the main important physics message is that everything depends on this dimensionless parameter, x, which is actually ratio of two scales, scale of the sphere and wavelength. And of course, there is different limits here, including geometric optics, Rayleigh scattering, in connection to the color of sky. But we are interested in this Mie of x of order 1 when we have this Mie-resonances. That's drawing from Mie. You can't believe it. It's a drawing which actually show different modes of this particle. And these modes can be composed, can be decomposed in two types, electric and magnetic. And we have electric and magnetic dipole modes as the major modes of the structure. So what is really exciting about that? If you look at the material like silicon, which is material of choice for optics, even for silicon, you can already observe these Mie-resonances invisible. And that's what people keep asking, where is breakthrough? That's breakthrough to realize that it works for silicon. Of course, Mie solution is arbitrary, it's epsilon mu, as theoretician put any parameters, but that works for silicon. So in silicon, scattering cross-section show peaks. And first peak is actually magnetic dipole resonance, not electric dipole resonance. So this is dipole, but for magnetic field. Only second resonance is electric dipole resonance. And actually, it's a well-known structure as we observe in plasmonics. And of course, basic idea is to take these resonances from Mie particles and actually applies it to the field of metamaterials to have magnetic and electric atoms based on this dielectrics. But again, you can immediately say, okay, we know field of nanophotonics based on plasmonic resonances and this localized or propagating plasmons. So let's replace all plasmonics by dielectric. And that's exactly what one of my young fellow tried to do. He went at SPP meeting, Surface Plasmon Polariton meeting, and tried to convince 400 people that we should forget about plasmons, you know, which was a silly idea. So what is the answer? Answer is, of course, everything, it depends on dimension. So if you take very small particles, like 50 nanometers, of course, everything dominated by surface plasmon polaritons and surface plasmon resonances. And of course, you don't see much from dielectric. Only if you increase the size of particles, you see, I did something wrong. You see effect of dielectrics. So you see that now that the silicon nanoparticles resonance is dominated, while metallic particles do not show sharp resonances. The reason for that is that this Mie resonance is a geometric resonance. So you have a sphere and resonance appear when wavelength inside of particles, which is lambda over n, refractive index of material, becomes comparable with the geometric size. That's why you need larger particles. If you look at Feynman, Feynman definition of nano, Feynman said everything below 100 nanometers, and it's nano. But here it's somehow nano, meso-nano, so you need probably put everything below 250 nanometers is nano. I know 300 nanometers now, because this is what we need. We need actually a bit higher particles to get these resonances. Of course, if you invent in optics materials with much larger n, then obviously you can shrink the sizes. And that's much easier to do for microwaves. Okay, what is the beauty of that? Of course, the idea to get resonance is to replace this magnetic and electric responses in metamaterials. That was the first things. But there is much more behind that. First of all, because size is already bigger, you can excite multipoles. In plasmonics, you know, people looking at different type of multipoles when they composed many particles, like oligomers type structures. Here, size of the particles are big enough to excite all higher multipoles. And of course, these multipoles are known after me, electric dipole, magnetic dipole, quadrupole, and so on. So now we can play with geometry of the particles to make that multipoles comparable. So why it's interesting? If you look at interference effect in physics, what is that interference effect? You have a source, one source, another source, and you see what will happen with waves which will be emitted by these two sources. To see interference, you should place the sources on a distance at least quarter of wavelength distance, you know, because if you combine them, it will be single source. Imagine that we have dipoles or emitters of two different types. And here exactly we have emitters of two different types, electric dipole and magnetic dipole, or quadrupole, electric and magnetic. Usually they're perpendicular, magnetic and because of structure of the field. And now because we have dipole of two types, we can coincide them, these dipoles, and like to look at interference from single point. This is amazing new physics, which you can actually use here because you can excite electric and magnetic dipoles in a single particles and work with the geometry to overlap them. Why overlapping is important? You know, for two source emission, you should be the same amplitude to see strong interference. You can't make it very different. Here, exactly when you do it the same value and the same amplitude, you see a lot of interesting stuff. This is one of the first, which was suggested by Kerker. That's why we sometimes call it generalized Kerker effect. When electric dipole interferes with magnetic dipole, so we can see unidirectional scattering. But actually, we can do a lot of things just because of interferences, because interferences are associated with every single particle. That's what we put in recent review with my former student, you know, because he was a part of KUDOS, Wei Liu. He's now associate professor of military academy in Changsha. Well, you can enhance many effects around magnetic dipole resonance because field penetrate inside, engineer near field, and also that was very surprising during last years that we can also go to region of high Q resonances. If you talk to people who know Mie resonances, they always said, okay, so this is a low order resonances, you need to go to whispering gallery modes to have a high Q resonances, much higher orders, but in the low orders, you never had the high Q resonances. But it's not true. You can actually do that. I just wanted to mention that there's still a lot of open things here because when you have many multipoles, interference can be very tricky. So recently with my collaborators from Russia, we look interference, not just electric magnetic dipole like here, Kerker effect, but just a bit higher order interference when you combine electric dipoles with quadrupoles, and you can see completely transverse effect. So you shine light on the particles and it reflects neither forward, no backward, just transversally. And that's all based on multipoles. This is microwave experiment. Anyway, high Q. From the very beginning of this field, we try to look what will happen with so-called hotspots, because hotspots, this is like a keywords in plasmonics. You create hotspots and you do a lot of sensing, Raman, enhancement, and everything. Hotspots is a specific words which all plasmonics people know, and we try to create hotspots. We took, with Arseny Kuznetsov, we took two silicon particles, placed them very, very close, and look what happens there. Of course, we see magnetic and electric hotspots in between, but because field penetrates inside, still you can't squeeze field very, very well, like we do it for metallic particles, which repel everything and concentrate in a gap. Of course, here you don't have magnetic spots, but still Q is a foot of 10. Now we move to specific geometries and we play, but again, this is one-dimensional system when we try to play with so-called one-half singularities at the edge of Brillouin zone, but still we can't push it too high. But in fact, the answer is there, and I was very surprised that we came across that, and answer is to actually use an interesting physics of so-called bound state in a continuum. And with this, you can push Q of particles or dielectric photonics to hundreds or even thousands. So what is a bound state in a continuum? People who are teaching quantum mechanics probably missed it completely. But it's a very interesting things which came from classical quantum mechanics, classical studies of quantum mechanics. In 1929, two pioneers of quantum mechanics, von Neumann and Paul Wigner, we published a very strange paper. That very strange paper was published in a journal which does no longer exist, like all scientific physics, published in quantum mechanics because they were replaced by European Journal of Physics. And the paper was the following. They solved Maxwell equation. That time many people tried to solve Maxwell equation. It was quite simple. In 2 or 3 dimensions with strange potential, oscillating potential, and found localized solution. Instead of repeating that paper, because not many people understand, I will put it on a cartoon to explain you ways of physics. So if you look at the quantum mechanics particles in the potential trap, this is everything what people know from quantum mechanics, from textbooks. So if your electron sits in a potential well, it gets traps and creates a discrete level of energy. Everything above epsilon 0, and that terms its propagating waves, so delocalize electron and correspond to continuum spectrum. That's very well known. So what happens if I change a bit potential? So what I will do with potential? I will look at the potential with such an interesting structure. So it will be oscillating edges of the potential. Again, I say that it's a cartoon. It's not explain everything. So, but these elements of cartoon you can find in many of the problems. So we see that now, of course, everything above is similar to that, everything below is similar to that, but in between, wave coming, and because of all these spikes, it experiences multiple reflections at that region. And you can play with reflected waves to adjust phase in such a way that you can get that states localized. That state will be fully localized, similar to usual discrete level of energy. It will see it in a continuum. That's why I don't know who actually first mentioned that it's bound state in a continuum, but that's what we now call bound state in a continuum. The question is it useful? Immediately answer no. Why? Because it's a single case with very special adjusted parameters which realize single point for potential which is actually delocalized, so in the continuum. So it's quite useless. If you look at mathematical definition of parameters, this means that formally Q is infinity of that state because it's shrink to 0, wavelength is 0, so it looks like it's absolutely useless. And some people, even in referee reports, said, okay, why do we need that? It's just completely mathematical curiosity. But we are physicists, we are not mathematicians. We don't need Q infinity, right? So who needs Q infinity? You know? So imagine now that I will deviate from this condition slightly. and I deviate to that condition, I hit another interesting effect. So now imagine that I deviate from the conditions, I allow tails, so it will be leaky mode. So leaky mode means that energy will leak, but also it will allow energy to come from outside. Now, energy from outside can couple to the states, but it stayed highly localized. And that's nothing but like fun resonance. So all this connected, actually. And even more, states which usually people in plasmonic call dark states, they are also bound state in a continuum. So, you will see it, and I will explain in a second. So that's very interesting notion in physics, which allows you to actually push Qs of these dielectric structures to very high values. Actually, it was interesting actually in physics to bound state in the continuum 92. It's for electrons in the super lattices. Federico Capasso was involved. You know, Federico was doing a lot of things. He was surprised that I found that paper. But then in optics, it was much later. People look at photonic crystals. And photonic crystals, you can see the strange states from interferences in the slab waveguide. And also people try to mimic the structures, actually combining discrete level with continuum level. This is for coupled waveguide arrays. And even I was involved in that for some time. But that's, I think the first it came to optics in the end of 90s, and then people pick up that idea, but also try to develop idea literally, so basically placing localized states into continuum state. But if you look at the types of these modes, this is the one which people study in photonic crystals, is a slab mode, which does not actually emit from both sides. Why? Because there is some symmetry protection. And of course, there is in-plane inversion symmetry, time reversal symmetry, which allows you to stay in plane. That's exactly what people find in photonic crystal community and describe there. But there is another type of this bound state in a continuum. And that was described by mathematician. And we call them, it's what we call them accidental. So it's a Friedrich Winger, again, Germans, but we describe it in purely mathematical paper through interferent resonances and bound state in the continuum. And there's a structure. If you have two modes which strongly interact, you can still achieve states with a very high Q and interferences. And for that, of course, you need some symmetry, but also up-down symmetry. Why this is interesting? And this is really interesting physics for us. Imagine that we have a dielectric resonator. So in electric resonators with relatively high Q, we can't localize anything because you need walls to get Fabry-Perot and some cavity, whatever, but in just a piece of dielectrics, nothing can be fully localized. So why? Because the typical state here, even for high epsilons, is a localized state with tails, which I call leaky modes. Now, imagine that I will design that resonator in a way to have two leaky modes. So if I will find two leaky modes sitting at the same space and frequency, I can play like in the potential with oscillating tails, with their tails and achieve state which will actually correspond to full compensation of tails outside. And this is the second type of bound state in the continuum. So we can take two leaky modes and adjust them in the way to kill the tails. It's really interesting physics, and it's associated with this mathematics paper in '85. So the question is how to find these two modes in the leaky resonators. There is a review paper written by our good friend Marin Zaljacic in 2016 about bound state, because he comes from photonic crystals and photonic crystal slabs and look at this bound state in the continuum. And then we have a box one, we said non-existence of single-particle bound state in the continuum in compact structures. Point is that if I would see it before, I start thinking about that, I would never start thinking about that, because that was their comment. And indeed, it was later paper by Andrea Lu, which was shown to get a wave trapped, you need to go to special condition, epsilon zero, epsilon infinity, so E and Z type of materials, which we suggested here. That was basically localized states for E and Z, which behaves like a metal and traps everything inside. However, we tried to look what happens, and accidentally we found interesting features associated with size of this oscillate, or of this resonators. So basically, I try to explain you very, very quickly. So if you look at the Mie solution is a sphere. Sphere easily can be replaced to disk or cube. It will be the same. A difference is that for sphere, we can find exact solution. For cube, we need to solve numerically. But let's imagine it will be the same strategic, with the same classification of modes. Let's imagine that instead of cube, I will expand that size of the resonator. So if I expand the size of resonator, I hit Fabry-Perot modes because they start to resonate in that direction. So it looks like, okay, you expand me to Fabry-Perot, but still everything should be classified in TEM, but not. Nature remembers where this modes comes from because this is donut mode of magnetic excitation and that structure. Only one dimension is expanding. And if you look at what will happen when you build that modes at full aspect ratio, you see these crossing points. And this is points actually crossing of Mie-like modes and Fabry-Perot-like modes, which generate this type of structure. If you look at that dark state, this is exactly bound state in the continuum. So by engineering the structure of single resonator, we can actually enter this field of high energy concentrator is absolutely open resonator because of these modes. So we published that paper, a purely theoretical one, and in order, then very recently now we combine these modes with Fano resonances and actually absolutely rigorously combine bound state in the continuum theory with Fano resonances and demonstrated that as soon as you approach bound state in the continuum, Fano formula collapses because it becomes ill-defined. It's clear because Q going to infinity. So at the point, we have like a hybridization of two types of modes. And due to this hybridization, one of the modes push dramatically up and become high Q. We call them quasi-bound state in the continuum because we are not really bound state in the continuum, but we are near one, but we actually allow us to use this high Q. And now if you look, all parameters, losses and everything for silicon nanocylinder, you see that we can still find the very high Qs of order of 200 for deep subwavelength regimes, and that's the way actually how to achieve energy concentration. So we had the recent confirmation with microwave theory in the microwave lab in ITMO University, St. Petersburg. So by just changing the size of this resonator in microwave, it's much easier to do it. We just have different sizes and adjust it, and you see that we observe dramatic enhancement of Q and energy concentration, but this is microwaves. If you go back to optics, of course, you remember that I come from nonlinear physics center, always was fascinated on linearities, and then we started Kudos, and Ben told me, what is the use of metamaterials? And we said, oh, we can show everything with microwaves. And of course, that was not enough for Ben, you know. So we need to do optics, and again, if you do optics, we come to splitter resonators, metals, lossy, plasmonics, a lot of problems. But here there is opportunity to go to optics. And one of the things we wanted to check, because we have high energy concentration, what will the conversion efficiency from the simple resonator turn to the position parameters of this bound state in the continuum? That was our theory paper. And of course, to do that, we need to use azimuthal beams to couple better because there is no QPM phase matching. So we need to couple specifically to the mode of these resonators. And that's what we analyze theoretically, and in the theory, because we can push Q to up to 100 or more, you can actually predict from theory second harmonic conversion efficiency of order of 1%. Can you imagine resonators few hundred nanometers without any QPM with a conversion efficiency of order of 1%? Just to give you some numbers, I have a table, but not that one. So when we first actually started Metamaterials, people tried to observe the conversion efficiency from this split and resonator metamaterials, and usual numbers is 10 minus 10. And once at plasmonic conference, I asked guys who reported about nonlinear effect in plasmonics, what was your conversion efficiency? And the guy told me, we never measured it because the fact that we see signal, it's already big achievement because it's so weak, you know. And now you can basically, with dielectrics, we can push it dramatically up. And then we recently tried to do experiment. I told them that I'm already experimentalist. So we have a nice nonlinear lab with a new laser fabricated by Berry. The only problem is that structures which are very nice were fabricated in Korea. So we still need places for publication and realizing of our ideas. That's basically a repetition of that theory. And I just wanted to attract your attention that, of course, a resonator sits on a substrate. We can't push it too far. So far we observe this effect with Q factor of 50. And these are experimental results. This is under review in Science right now. And you see, depending on type of beam we use to excite this mode, so we use azimutally polarized, radially polarized, coupling to the mode is different. So with, around the point of this bound state in the continuum, we call quasi-bound state, we see that very efficient coupling to azimuthal modes. This pushes us very far. And with this relatively small Q factor due to, than predicted. This is, you can compare recent observation, and this is type of mode used. This magnetic dipole mode, which was used originally, and quadrupole modes still give much lower numbers. You see that this is conversion efficiency of the best results so far, but still using bound state in a continuum, you can push it to 0.1%. It's because we can't actually push Q factor. We know how to increase it to 120, but that's already next step. So in brief, I try to explain you that this even single resonator can be very efficient for generation of nonlinear effect, but of course, people interested to go to metasurfaces. So some like a single particle approach, it's interesting, but it's really nano optics, nano institute subject, but metasurfaces have much broader applications. Metasurfaces is a really interesting story because, in fact, people initially said, okay, nothing surprising because these are two-dimensional metamaterials. So metamaterials just put on one plane. It's yes and no, because in metamaterials, the main concept which came from Pendry was we have very small structure and we look at much larger wavelengths. So we use average parameters. So average parameters means that we can do what the mathematicians call homogenization and introduce these parameters which be responsive for that. And for that, of course, three-dimensional, very attractive. Nobody interested in average parameters here. Why? Because it's a structure, planar structure, mainly we use a normal propagation. Average parameters would be like if you propagate it along the surface, so nobody cares. So this is kind of very, very advanced diffraction gradient. Some people ask me in a popular question, what is a metasurface? I show them picture, which it's in New York, I made it just myself. And what is the most amazing about that picture? You can't believe it. It's made in China. But this is the idea of metasurfaces. So you structure a surface which performs some part of functionality, particularly we stop from slippery. But in optics is also patterning structure. I use that slides, which Federico already not using, but I borrowed from him because very useful for me already for some number of years. This is explanation of Federico, what is metasurface. So we use Huygens principle. We basically look at particular surface, and according to Huygens, every point of that surface becomes a meter of the secondary wavelength. And now it's clear if I want to do something with beam here, I need to modify the surface to actually change these discrete emitters along the surface. And of course, that metasurface with change emitter should be patterned. It should be patterned, and this should be similar to what people use for gratings, but it should be patterned in any type of different way which you want. So basically, you introduce this effective A number which is associated with patterning of that surface. And the great achievement of Federico as always, people say, if it's simple, they said, oh, it was known. And of course it was known, but can you show me that formula before, you know? And so Federico corrected Snell's formula, and that was in his first science paper. Of course, in terms of gratings, people try to write K vector directly because it was periodic, but now any type of patterning in produced phase, and this is actually how Snell's law look like. Now we can actually control reflected wave in any way we want because we pattern the surface. And that's the beauty of that, because it's not metamaterial, because we are not interested in average parameters. And of course, it's not diffraction gradients, because it does much more and can do much more. We can actually introduce different mode there. So it's kind of what people still metasurfaces, a very popular topic. From the very beginning, we ask a question, okay, so in Federico's picture, it's a Huygens principle, but what happens with reflection? Nobody discussed reflection, but it should be. And our idea from the very first days was to kill reflection. And we use this Kerker effect, which I mentioned for this interferences of two types of resonances. And this is the physics. So basically, we use electric dipole, magnetic dipole. We play with sizes, superimpose them, and try to get unidirectional scattering. So this is a ray of electric dipoles. Of course, if you take a ray, we will meet to both sides. The same happens with magnetic dipole. That's well trivial, well known, and because we emit a specific shape of radiation, it's very clear. But what happens, as I mentioned, if I take different of them and superimpose them in each single point of this surface, I will superimpose them, and what I will achieve really unidirectional scattering, because waves from outside, from two types of sources, will be completely suppressed. That was our initial idea. And it was also next interesting discovery which we made when Isabel Stoide was as a postdoc in our group. We need second parameters to actually move these resonances. And second parameters easily comes from disk. In a disk, you have two parameters, height and radius. You can play with them. You can put in metasurface, and actually see that if you if you work with different geometry, changing parameters, for example, diameter, you have overlap of these two resonances. And that's what Isabel first demonstrated. But the funny thing was that now we, of course, can calculate everything, but that time we were not able to estimate influence of substrate. And we sent Isabel to San Diego to work with Ziegel Brenner, our friend. And Isabel is German origin, so what Germans will do? We fabricate many, many structures. And that's exactly what she did, and found one, because now we can calculate and do it much, much better, just fabricated just right structure, but that time she fabricated around 100 and the different structures and found the point when we overlap because of effect of substrate. So what these surfaces are called Huygens surfaces, and we demonstrate 2-pi change of phase, and of course very high transmission. And that's what was in the paper which we published in 2015. Still remains the most cited paper, Advanced Optical Materials. But the question was, when I presented at that time, people asked me, okay, this is a similar question like a bound state in a continuum. It's just for one frequency, it's just for one size. Nobody knew that because it's just like coincidence of parameters. And I even don't remember if Ben asked that question, you know, when we presented for Kudas, like opportunity. And then, of course, it was a question how to make them broadband. It's really everything comes from these interferences. And I will very briefly explain you how to make it broadband. I mentioned already that there is a Mie and Fabry-Perot interesting correspondence. So Mie corresponds to this three-dimensional Mie solution sphere, or two-dimensional Mie solution is a rod, infinite rod, that's all done analytically, and this is done numerically. But what will happen in between? As I mentioned, when I increase size, I have hybrid modes, combination of Fabry-Perot with Mie resonances. Coming back to the picture, I have a single magnetic Mie dipole mode when it's small. So it's a dipole donut mode here, and it's a single mode which comes from Mie theory. If I extend size, I include Fabry-Perot mode. So Fabry-Perot brings another magnetic dipole. It will look exactly like here, but here it will be quantized because size is larger. And that's exactly what's happening here. So basically, we look at the solutions, and for decomposition, I see the second magnetic dipole mode. If you look at the structure, of course, you see this is normal structure with a fundamental mode, and this is this next order mode. I know you should look at magnetics. This is magnetic dipole, similar to sphere, and this is next order, which correspond to higher modes. And that's we want to use for metasurfaces. And how we want to use it for metasurfaces? We want to look at taller rods, because smaller rods will not work. And what we do, this is exactly what we have for Kerker conditions for specific orientation. So this is Kerker condition, 100% transmission for specific wavelength in transmission. Now I play with size and I trap the second magnetic dipole mode. This is actually a log scale of the same picture. So you see the sharp resonance, and this is where we sit with the Kerker condition and Huygens surface. If I trace the second mode, I have two features. In each of them, it's actually our Huygens condition. But each of them will be Huygens condition with very high transmission. But if I don't want to have 100% transmission, I work in between, I can expand the range of operation. Not with 100% transmission, but still very high. How high, I will show you in a second. So that's the idea of broadband. And actually, actually, this is a physics of many papers which you never will read in the paper. For example, I came to Federico. Federico, of course, switched from plasmonic to dielectric and said, Federico, how do you optimize your structures? He never tell you why we're so tall and why plasmonic is so thin, you know. Of course, you need quarter wavelength. It's not just very thin. And he said, oh, I have 4 brilliant Chinese postdocs and we do optimization, you know. But again, we do optimization and we increase size and come to the same physics. Anyway, that's how we do it. And if you look at real transmission, we expand it substantially. So when we get a paper about that, we got a problem with publishing, and I mentioned to Ben, and he almost killed me, said, published there. It's still most published paper in APL photonics, most cited paper in APL photonics. And we published it, and he kept promises and put it on the front cover. So we are very happy with that. Maybe 200 citations already. So that's we demonstrated how half-wave plate work and quarter wavelength work, the paper, and really was interesting milestone. Now, if you put everything in terms of performance, again in transmission, reflection a bit different. So initial concept came in 2012. It's a science paper of Federico. If you look carefully, what we demonstrated, efficiencies were very, very low because this gray means plasmonics. So we use plasmonics, thin, but efficiency low, losses hitting everything. People switch to dielectrics. I hardly believe you will find paper now publishing some transmission with plasmonics. People do reflection, absorption, that's good, but for transmission, you need to do dielectric. This is blue, it means dielectric. People switch to dielectric. And where we are, okay, so this is the maximum because this particle sit on the substrate, this transparency of glass plate, and this is we are. So if you know how to engineer that, you can basically make them almost transparent. And this is very high transparency surfaces. But again, remember that we can engineer phase between 0 and 2 pi. We have 2 resonances. Each of them has a pi jump. We can put everything on that plane. I don't have many examples, a lot of different applications. I just have only a few examples from our group. Recent advances. This is also our kangaroo, which was an optica in memorandum. So we can do optical communication. That was Ben's dream. Unfortunately, it came a bit late because we now made experiment with, you see some suspicious names coming from Buddhas. Actually, Magnus was in Canberra for some time, so, but it's again, Peter Anderson, you can understand that, you know, where it comes from. So this is metasurface used to do spatial multiplexing and multi-mode fiber. And it still was not accepted by telecom community. We got the problems to publish it in Optica. We can basically create metasurfaces. We print any type of images for different type of polarization and wavelengths. This is without any optimization. You see that level of transmission, and it covers free telecom bands. So you can do a lot of application using this highly transparent metasurfaces for different type of special mode multiplexing and multi-mode fibers. Now we can do quantum. That's a project driven by Andrei Sukharukov. So we can do quantum, we can design a surface to do multi-photon state tomography, and particular was some efforts to demonstrate these ideas for photon pair experiments, and we use basic geometric phase type of structures, but again, highly efficient in terms of transmission. And then I come to another interesting topic also associated with bound state in a continuum. This is bound state in a continuum in metasurfaces. If you look at the papers published, people somehow reported high quality Fano resonances in metasurfaces. We try to play with different type of geometries. Oh, I did something wrong. Yeah. And in fact, we have a summary of some of these structures which people discuss. So we discuss this is from Eagle Brenner. So you see some kind of square with a small tip. This is slightly asymmetric bars, shifted zero. So people discuss some structures which demonstrated very high quality resonances, what they call through Fano. When we look at that, we realize that it's all these separate discoveries can be actually classified under this notion of bound state in the continuum. But it will be another type of bound state in the continuum, as I mentioned, similar to photonics lab. So what is the difference here? So if in bound state in the continuum in photonics lab, we have a guided layer, structured, and we have incoming radiation. If it's normal, it will not couple to the mode. You need to incline it to get coupling to the mode. But of course, inclination, specific angle is not interesting for metasurfaces. So how to couple it from normal propagation? And that's actually here. We need to change symmetry. You need to break symmetry in plane to couple it with the incoming radiation. So normally propagating wave will couple depending on the symmetry parameter. And that gives you a hint. This is a symmetry parameter. This is the control parameter of your bound state in the continuum. That's exactly what we demonstrated in that paper. And we put all these cases on one curve. You see that this is quality factor, which is a square inverse of a symmetry parameter. Of course, the symmetry parameter should be defined properly, but basically everything can be scaled, and we can get any value of quality factor that we made previous papers on that simple diagram with scaling factor. Why is this interesting? This is interesting because you can control transmission and reflection of surfaces. So what is basically, this is a kind of Fano resonance. So this means that if you have a surface and you come to these conditions, you may have either full transmission or almost full transmission or almost full reflection. This is very useful functionality for different applications. It's not like a usual magnetic mirror when we have one resonance, when we reflect everything for single frequency. But it's Fano means that you can do it both, transmission and reflection. That's very useful. There are many applications. I was actually pushing sensing application, and that's our paper with Altuh Hatis, people working in photonic crystals, we know her. She has a very nicely established lab for biosensing in Lausanne. It's EPFL, which is the French version of ETH. And we did that interesting experiment. So we designed a metasurface which consists of different pixels. So each pixel is a metasurface with these tilted bars. Tilting means that by changing the angle, we produce specific resonance, which we may control. And these pixels are important because each of them gives you different resonance. So basically, the entire structure produces a comb of resonances. Comb of resonances now in mid-air will interact with vibrations of particular molecules. And if you drop a substance there, depending on type of vibrations, we are sensible to particular resonances. And, and you actually can observe that depending on the type of your substances, you will see different response of this metasurface in terms of colors or resonances or flashing, whatever you will design. So we call them barcoding of barcoding sensing, and actually does not need a spectrometer, just done very simply through this imaging of the surfaces. And we push further this activity, so that's basically not pixelated by simple metasurface which use different angle. And this is also what we apply for hyperspectral biosensing, analyzing a lot of data and trying to summarize the data. That's all just appeared recently in Nature Photonics. So that's very good for sensing because it produces specific resonances. And I didn't mention there because we are working on that. You can make these resonances depending on chirality. And that will be big breakthrough because chiral sensing is still a very big area which people do not have a clear answers. So what else we can do? We can move to nonlinear metasurfaces and design different type of nonlinear surfaces which are associated with transformation of frequency of light. And this is done with a different approach, not using very phase, but just designing different type of structures. Of course, each of them support electric and magnetic dipole modes. This is very important because some combination of that, this is multiple presentation of multiple contribution, magnetic and electric modes. And what we can do, we can basically design any type of nonlinear lens which will convert efficiency. This is example of nonlinear beam deflector, which composed of this highly transparent metasurfaces with a high energy conversion. I think conversion was 10⁻⁶. Here we observe third harmonic, so basically majority of third harmonic signal was going to this diffraction order with very high efficiency. That was work with Barry. I don't have time to develop it further. I have a topology, but it's a relatively long part. I just want to mention that topology where Ben is involved is very important because it involves a lot of interesting, not very conventional knowledge. For example, if you look at these two men's, you may say that we are different, but in fact we are topologically equivalent. So you can't remove hole from donut, but here you can, through transformation, make them similar. And this is topology, which I think you probably heard from Ben, but I just don't show you too much. I said that all-dielectric photonics is very suitable because we play with two types of modes, electric and magnetic, and we can create a kind of pseudo-spin for the structures, creating the special time unidirectional modes sitting on the surface. That's our model. I just wanted to say that we move to nonlinear properties because nonlinearity allows you to break time reversal symmetry and observe interesting effect. We have an interesting paper just came this year about nonlinear light federation and topological structures, and I come to conclusion. This is our two-dimensional structures. Anyway, I just don't have much time to discuss. Saying that metamaterials still alive. This is a field which is evolving, and now it evolves to meta-optics. So even people do not accept it like very common knowledge, but it's actually many examples that we evolved in that direction. We are not interested in average parameters anymore, but we use magnetic response. And of course, for that, you don't need metals. You move to dielectric structures, and where you can actually employ magnetic response from Mie-type resonances. And topology is very natural extension of this knowledge. This is a review paper a few years ago when we put the tables which I showed. Thanks for your attention.
Okay, I didn't want to actually disturb. I know everyone.
It's extra 15 minutes. Probably it would be unfair.
Objecting to it having this seminar going for the whole day. But because we are recording this, and the recording will be available on the Sydney Nano website after this, I like to, if you are having a question, please ask it in.
So your questions will be historical. That's what you want to say.
Historical questions, basically.
Thanks, Yuri. That was a great talk. In terms of fabrication, I presume ultimately you want largish surfaces. some of your devices were fabricated using electron beam lithography, which is kind of small area. You guys looking at how to fabricate larger areas?
Yes, there are different facilities, but at the moment we did not use, first of all, quality of fabrication is important, because in the theory, you should just change angle and go to infinity. Come on, you know, never happened. But also we discovered even more interesting feature. So making angle smaller does not improve things, because you have radiative and non-radiative losses. And interplay between radiative and non-radiative losses is very important, because for smaller angle, quality of fabrication is lower. So somehow, and that with sensing work, we fabricated many structures. And angle, if you remember, scaling parameters was actually size, not angle. Angle was fixed because empirically we found angle, which is not very small, with large highest Q of order of 200. So we change only size for scaling, not angle, because there is kind of trade-off between all these effects. As soon as you go for larger sizes, you need to imply different methods or different quality, but quality is important. You can't just fabricate it in one row. That's, yes, there are different approaches. We collaborate, for example, with Leibniz Institute in Vienna, which fabricate on the bigger sizes, but still everything is relatively small. Yeah. In terms of application, of course. And of course, everything is cost, you know, and to make it user-friendly and available in every pharmacy, it should cost no more than $5.
Yuri, for these structures, how large is the effect of the surrounding refractive index? And I'm thinking of, for example, embedding the structure in a gas cell and changing the gas pressure to provide tunability.
Good idea. I mean, of course, it's sensitive because it depends on index difference. And of course, it may work. I don't know if anyone who actually suggested that. Changing, for example, with a layer of liquid crystal that's relatively straightforward. Difference is that layer should be relatively high, you know, quarter of wavelength that and probably several wavelengths for more thickness. But with gas, I didn't know about that. So maybe gas will give you new opportunity for metasurfaces in general, not only for these resonances. Yeah.
Yuri, your outstanding presentation. We heard years ago from Capasso work he was doing with Google and Google Glasses, and there are lots of applications. We hear from Jinping Tsai in Taiwan. He's going to be a plenary at Cleopac Rim. Where do you think the industry is pulling this? And where do you think the killer application is?
I know it's a very natural question for you. I'm a fundamental scientist, you know.
You must have a sense of what.
Yeah, there are, people are pushing this flat optics. Flat optics is a great opportunity, but you can do a lot of things without any flat optics. And that's the problem which we got with reviewers from fiber community when we start to publish all this multiplexing, spatial multiplexing work, which we believe, they told us at least that it shows records data for this transmission and multiplexing speed, whatever. Referee literally wrote us, I don't care about size. I have fiber optics. That size is fine for me, meter, but I don't need to squeeze it to just flat surface. I believe the most interesting recent development is possibility to make them tunable. Tunable, because the tunability of lenses, of course, it's impossible. But if you make it flat, make it active and tunable, that's maybe where it will go. That's my possibility to bring something new, because just like optical elements with flat size does not look very attractive at the moment.
Except that it reduces the cost and complexity of manufacturing optics. I mean, that's what you hear.
About cost, you know.
Yes, that's right.
If you use EBL, you know.
Well, sure, you necessarily need.
Depends on device, of course, yeah.
But I think the Finisars of the world would much prefer a flat element that doesn't need machining that a piece of optics.
But this is for specific applications. I'm trying to address you, yeah. So we are moving to active field, you know. In active, for example, what we are trying to do, we use metasurface and cover by Halid perovskite, so to get emission. So basically, this bound state in the continuum can be useful for lasing. You know, there are a lot of possibilities in this active nanophotonics, but different people have different contracts, working for different companies, but it depends on specific application. That's my feeling. I was interested in physics, you know, which I explained to Federico, and he loved it. He said, "Wow, my 4 postdocs just observe it, but never explain it to me."
Okay, I think we'll leave it to these 3 questions, and if you have any other question, I think the lunch should be available outside. We have a networking event after this, so you can ask questions offline. Can you please join me again thanking Professor?
Thank you very much. Thanks for your interest. Yeah.